Welcome to Math 31. This is going to be a lesson on the derivative, so this is really the introduction to Unit 3. You will see that much of the early part of this unit will be picking up with what we were doing in Unit 2 at the very tail end of it, so it really links up nicely. Critical stuff, the derivative is really the foundation for what you work with in this entire unit, and in fact, or the entire course, excuse me, and for any other calculus work you do in the future. So it's really important that you get a handle, not just on the math of this, because the math demands algebraically are considerable, but also the concepts, because that's going to really come into play later on, your understanding of these. Now there really are what they're often referred to as two fundamental problems of calculus. And the second one we'll cover when we get to the integral, and that's area under curve. The first one has been, dabbled in by us previously, but that's where you're dealing with the slope of a tangent line. And it may seem like a trivial matter, but in most science applications, particularly physics, you always work up to a certain level. You work with the assumption that acceleration is constant, is uniform, and that gives you fairly easy work in terms of finding the slope of the lines, because they're always lines and you can get the slope. And considering that when you're dealing with the distance time graph, you want the slope because that represents speed. And if you have a speed time graph, you want the slope because that's acceleration. And all that is fine and dandy as long as you've got straight lines. You can always get the slope. But what happens when the lines are changing? And if you think of real life, just for a minute or two, I don't recommend you dwell on that topic for too long. But if you do, you'll probably realize that usually speed and acceleration are in constant motion. They're not staying the same. They're in flux, which means regular physics can't handle those things too well. And that's where calculus comes in, because it deals with dynamic systems that are constantly changing. So you're able to find things like instantaneous speed, instantaneous velocity, or rate of change. At what rate is the volume changing as time changes? Things like that. So it really becomes significant, and you'll some point get to a stage where you cannot imagine life without a bit of calculus. And the two of the originators of the derivative, this part of it, were Isaac Newton, which most people are familiar with, and then also a fellow called Leibniz, who pretty much concurrently developed some of the theories. And we'll be referring back to those guys as we get a little deeper into the unit, or actually very soon. Now, this is what we do know. The derivative of a function, f at x, is f prime at x. And this is defined as the limit of f at x plus h minus f at x over h as h approaches 0. That's the derivative. And we covered that at the end of the limits. And that solving limits by first principles is finding the derivative. Now, that method that we were doing in the previous unit can't last forever because it gets too complicated. So we do eventually have to come up with easier ways, which is what we do in this unit. And naturally, this is only true if the limit exists. That also comes into play fairly soon. So this finding the limit, or the slope of the tangent line, using this method is the derivative. And this derivative is a function itself. It's derived from f at x. And very important, it represents the slope of the tangent line at x values of f at x. So it is a formula that allows us to always, always, always figure out what the slope of a tangent line is. And the other thing that we could look at it in terms of is that it represents the rate of change of y with respect to x. Should make sense because m, the slope, really is doing exactly that. At what rate is y changing as x changes? Now this can be done in terms of other variables as well, which we'll also do, particularly with applications. So how is y changing as x changes? The process of doing this, of taking the derivative, is called differentiate. So you'll be asked to differentiate this, differentiate that. Now the notation, very important. And you're going to see variations of it. The first thing that we've seen, f prime at x and y prime, very simple. And they do represent the derivative, and we will use them where it's appropriate. So what's going to happen when you're dealing with notation is you're going to have to make decisions on what type of notation you want to use and when. Very important. And when I first took this, I paid no attention to one form of notation versus the other. And I didn't take it very seriously for about a month, maybe not even that long, and then I was educated. It really matters. It really makes a difference which type of notation you're referring to, particularly when things start getting complicated and you're working with more than one variable, which is going to happen. And this brings to mind the next type of notation, which is generally referred to as Leibniz notation. And we call this dy dx. And it refers to the derivative of y, of the y variable, with respect to x. So it's very useful, you'll see, because it gives you it tells you which variable you're taking it with respect to. And it matters, as I said, when we get more than one variable in play in the same equation. So dy dx. And then you'll see dy dx written like this as well, too, less common. Now, typical question then will go something like this. Given a function y is equal to x squared, find the derivative of y with respect to x. So the way we do that, we would take the derivative of the function x squared with respect to x. So to further complicate things, I'm basically throwing everything at you right away. We call d dx the operator, or the derivative operator. And it tells you what you take the derivative of. So in this case, we're taking the derivative of the function x squared with respect to x. And we haven't worked out a method, a fast method for this, so some of you are doing first principles on it. But take my word for it, it's equal to 2x. So the derivative of y with respect to x is equal to 2x. So we do get a method for it, so just hold tight with that. But the only way we can do it currently is that first principles method. I'm really just concerned about notation, though. So the derivative of y with respect to x is equal to 2x. So this represents a formula that we would use in order to find the derivative of, or to find the slope of the tangent line for all x values along that function y is equal to x squared. Now the next basic topic, I don't want to get, until we get the methods down, I don't want to go too crazy with this. But the concept of differentiability matters quite a bit. This might make sense to you. If a function is discontinuous at x equal a, then the slope of the tangent line, which I'll call f prime at a, so the derivative at point a, is undefined. That should make sense to you. If the point doesn't exist on the curve, or it's discontinuous, it's a hole in the graph, then how are you going to find the slope of the tangent line? You can't do it. So it would imply then that the function is non-differentiable at x equal a. So one of the things we're going to do early on in the unit is pay attention to areas where the function is differentiable or non-differentiable. Seems like a small thing. Down the road, it matters, however. If the tangent line is vertical at a certain point, then f at x is non-differentiable at x equal a. This also might make sense to you because a vertical line, the slope of the tangent line, is undefined. So because the slope of the tangent line is the derivative, therefore it would be non-differentiable at that point. And functions are non-differentiable at sharp corners or transitions. Now this is something that will require a bit more exploration later on. We'll actually show this. But if you take a look at this graph, for example, that we have right here in front of you, you're pretty much your classic absolute value function. And if you were to examine the x equals 0 point and try to make some sense of this. Now this, we have the equation for it. By inspection, the derivative of this function is equal to -1 for or when x is less than 0. Might make sense because the slope of the tangent line is equal to -1. So that is the derivative all the way until we get to x equals 0. And then, if you were to take the slope of the tangent line when you're on the other side of 0, so for x is greater than 0, you'll note that the derivative is +1 because the slope of the tangent line equal 1. So the derivative is -1 and it's +1. And then the obvious question would be, what about x equals 0? So we've established that this is differentiable if x is smaller than 0, and it's differentiable if x is greater than 0 because we were able to get the derivative. We were able to get the slope of the tangent line. And if you were to work out left-hand limits, the left-hand limit, so the limit, and be careful, I'm not taking the, I'm taking the limit of the h value approaching 0. So in other words, this is the derivative. So the derivative of this function, as I approach 0 from the left, as I get closer and closer, again h representing the horizontal distance between the two, the derivative will be -1. And then you'll see where this is going. The right-hand limit, so the limit as h approaches 0 from the right, f at x plus h minus f at x over h, this is equal to +1. So the derivative from the left is -1, the derivative from the right is +1. And the left-hand limit does not equal the right-hand limit as x gets closer and closer to 0. So you could say this, actually I'll say as h approaches 0, is more accurate in terms of h. So therefore, non-differentiable. And x is equal to 0. Now, in general, these sharp corners indicate non-differentiability. So you can tell this on other graphs, which we're going to see later on. When you have a little sharp point, it means that it is not going to be differentiable. We look for the smooth curves. There it will be differentiable, but not the sharp corners. Now I'm going to shut it down right there. This is just an introduction to this. The next lesson we'll pick up and do a geometric representation of this, and we'll go a little bit further. So thank you for your time.